Okay, once again, today's lesson dealing with circles, we're still talking mostly about segment lengths in circles. On Wednesday, we'll move into talking about angles in circles. So, first of all, a little bit of vocabulary. A chord of a circle is a line segment whose endpoints are on the circle. And in this blip up here, I'm referring to problem 1, which isn't on this screen, but it is in your notes. Segment RP, for example, is a chord. It's just a line segment in a circle. Its endpoints are on the circle, right? So let's backtrack. I know I'm saying that today's lesson isn't about angles, but I want to make sure that we see the relationship between angles and chords. Remember, way back in chapter 10, when we found circumference and when we were finding arc length and area of a sector, one of the first things that we talked about was how the measure of an arc, first of all, remember it's 360 degrees all the way around the circle, and because of that, we realized that the measure of the central angle is the same as the measure of its arc. So if I have two central angles that are congruent, you don't have to sketch this. Do a better job. If that's the center of my circle, then I know that all of the angles in that diagram are central angles. Well, remember also, vertical angles from way back in chapter 1, vertical angles are congruent. So if these two angles are congruent, and I know that the arcs related to them have the same measure as the angle, it should make sense. Two central angles are congruent if and only if their intercepted arcs are congruent. One of the things that we'll talk about is that a chord has a related arc. So this chord and this chord, you see, would also have to be congruent. So two central angles are congruent if and only if their related chords are congruent. And then finally, we kind of see that everything is connected. The angles are connected to their arcs, the angles are connected to their chords, and the chords are related to their arcs. So two arcs are congruent if and only if their related chords are congruent. So in this lesson, a big chunk of what we're dealing with is seeing that relationship between the central angle, the chord, and the arc. If one pair is congruent, then the other two things are congruent. And we'll see that in problem 1, where they're simply asking us, what am I allowed to conclude based on what I'm given? We have on the screen what we need. Okay, so in problem 1, notice what we're given. That segment VT is congruent to segment RP. Well, those are chords. And if chords in a circle are congruent, then I know their related central angles are congruent, and I know their related arcs are congruent. Yes? Say that again, I'm sorry? Segments RT and VP are also chords. They could be, they probably are diameters of the circle. So just based on those two segments being congruent, I know that arc RP will be congruent to arc VT. Let me rephrase that. D is definitely the center of the circle. So I know that angle VDT is congruent to angle RDP. Of course, I knew that already. Like I said before, they're vertical angles. They've been congruent since chapter 1. Pretty straightforward. Now, how do we use this to find segment lengths? We've talked about perpendicular bisectors before. We've talked about the term equidistant before. So if I have two chords that are equidistant from the center of the circle, what do you think might be true about those two chords? They'll be congruent. Two chords are equidistant from the center of the circle if and only if the chords are congruent. So wildly, easily, in problem 2, we notice that these two chords are equidistant from the center because their distance is both marked as 7. So I know those two chords are congruent, therefore the value of A is screaming at you. 6, a little louder screaming, yes. The value of A is 6. Those two chords are going to be congruent. They gave us part of the second chord. And you might be noticing from this diagram a property that we're coming up on the back of our notes. And once again, these properties are very, very closely related. We're talking about the perpendicular bisector of a chord in pretty much every single property. Okay, so if a diameter is perpendicular to a chord, then it's bisecting the chord in its arc. So I might have this as my if. If the diameter is perpendicular to the chord, then it bisects the chord. If I know that the diameter is bisecting the chord, then I know that the diameter is perpendicular to the chord. And if I have a chord that has been perpendicular bisected, then I know that perpendicular bisector is a diameter. That perpendicular bisector is a diameter. So some of these properties may seem kind of, well, duh, it's true. But what they allow us to do is to use one to conclude the other, basically. Wildly straightforward lesson. You'll have plenty of time to get started on your assignment. We have what we need from the screen. Okay, so in problem 4, we're finding missing segment lengths again. And once again, just like in last week's lesson when we were talking about tangents, tangent, remember, was perpendicular to the radius drawn to that point of tangency. So we use a lot of Pythagorean's theorem. And you're probably seeing here, right triangles, I'm going to find some segment lengths. We're using Pythagorean's theorem. So how will Pythagorean's theorem get plugged in part A? What squared plus what squared equals what squared? Grace? Beautiful. 6 squared plus x, whoops. 6 squared plus 5 squared equals x squared. The instructions say round to the nearest 10. $7.8. Someone else, please. How will Pythagorean's theorem get plugged in part B, Helena? Beautiful, yes. Even though that 9 isn't placed in the triangle, it's a radius, and you know that all of the radii will be congruent in a circle. So x squared plus 5 squared equals 9 squared. $7.5. I do have a daily quiz on Socrative. I'll be activating that momentarily.